So we have been studying logarithmic equations, how to solve them when it's a log compared to a log, when you have a log compared to a number, when we have even two parts of the equation in exponential form where the bases are the same or can be rewritten the same. With a log equation, when we finish solving a log, we end up with like a very specific value for x. Sometimes we have two very specific values. If we go through and we check them, we might find that one of these may be an extraneous solution. Maybe both of them are extraneous solutions. But at the end of the day, we do have a specific value that x is allowed to equal because it is an equation. Equations deal with things like equal signs. So every equation contains an equal sign. What we're going to look at today is something called an inequality. And that's where you have your less than, greater than, less than or equal to, greater than or equal to. When I'm looking at an inequality, all of a sudden I go from having, let's say, here's my number line. I go from having a single value from an equation, x equals 8, x equals 3/2, x equals -6, to having an infinite amount of possibilities. So, for example, if this was 6 and a singular value, we could have solved an equation that simply said that x had to be equal to 6. One answer, the end. Well, when we look at an inequality, and let's say we have something like x is less than or equal to 6, all of a sudden we have all of these possibilities. Any value less than or equal to 6 can be chosen to represent your variable when you're dealing with an inequality. So you have an infinitely many number of possibilities. With that, there are certain restrictions that come with logs. So on the front side of our notes, we're going to look at just comparing like exponential function to exponential function. On the back, we're going to take a look at when we start to add logs. One thing I want us to think about is our base. All bases for our logarithmic functions, most of our exponentials that we're working with are going to be greater than 1. So 2, 3, 4, 5, 6. If we are dealing with a base that is bigger than 1, our inequalities are true. So if you see a less than, it is a less than. If you see a greater than, it is a greater than. The issue comes when we have our bases that take on a fraction form less than 1. So 1/3, 1/2, 6/8 or 6/7. When we think about numbers that turn from whole numbers into fractions, when we're looking at those properties of exponents, it's because that exponent took on the form of a negative. So we have talked about this before, like 2 to the -2 power. That's the same as saying 1 over 2 squared. So it's a location issue, right? Which is the same as 1/4. So if I see something with a base of 1/4, I can always come back and rewrite it as having an exponent that was negative. Now the thing is, when I'm dealing with inequalities, negatives have a tendency of turning an inequality around. So eventually if you have to multiply or you have to divide by a negative value, your inequality sign will switch because it goes from less than to greater than or greater than to less than. So if you have a base value, whether it's an exponential function or whether it's a logarithmic function, and you have an inequality, then your inequality symbol gets switched around. We're going to go ahead and deal with that negative up front. It allows us to just kind of take care of business ahead of schedule. So let's look at the first one. It says find the solution set of the inequality and then check your answer using a graphing utility. That would be Desmos. I'm not going to check it. I'm just going to kind of give you the information and then you can check that using Desmos. So the first thing I'm going to look at are my bases. They are not the same. However, they can be rewritten with a base of 5. So this can be written as 5x. It's greater than 125 is the same as saying 5 cubed. X plus 6. Because my base is greater than because my base is greater than 1, my inequality tells me the truth. So I'm going to keep my math using the same inequality symbol, unless I have to manipulate it in such a way that it flips. But as of right now, I'm going to make sure that it stays the same. So when I'm looking at my exponential function, I see that my bases are the same. Oops. My bases are the same, which means that my exponents can be compared to each other. So this becomes x is greater than 3 times x plus 6. Because whenever I have a power raised to a power, I can use multiplication to combine those. So that gives me x is greater than 3x plus 18. I'm going to solve for x just like I would any multi-step equation, but I want to be careful in case I have to do any multiplication or division that involves a negative value. I want to be cognizant of my inequality. So I'm going to subtract 3x from both sides. It gives me a negative 2x is greater than 18. I'm going to divide by negative 2. And right here, if you multiply or divide by a negative number, then your inequality sign changes direction. Your inequality sign, we call it flipping or changes direction. It means it goes from being less than to being greater than, or from being greater than to being less than. So I have divided by a negative number. So instead of being x is greater than, it now becomes x is less than negative 9. And because we are dealing with exponents, we know that exponents are allowed to be negative. So I have these two together. This is a great place for us to put a set of looky eyeballs so that it tells us where we need to go back and look. Let me redraw those. Those look really bad. A set of looky eyeballs. So we can go back to our notes and we can look and see what happens when I multiply or divide by a negative value. Again, we are dealing with things in exponential form, so I don't have to go back and look about or ask myself, is there any additional restrictions? Is there anything that has to remain positive all the time? So my value is x is less than negative 9. So if this was a number line, here is 0, here's negative 9. I'm allowed, I can't choose negative 9 because it's not less than or equal to, it's strictly less than. But I can pick any number smaller than that, and this inequality would remain true. The comparison would remain true. Whatever value I substituted in for x, the left side of my inequality would always be greater than the right side. You can also rewrite this if you wanted to in interval notation. So you could say from negative infinity all the way up to negative 9. Either option is okay. But look what happens when we look at question B. I now have an inequality that deals with a base that is not greater than 1. It is a fraction. So when I go to rewrite them, I'm going to compare 3 and 27. Well, 1/3 is the same as saying 3 to the power of negative 1. That's 2x plus 9 must be less than or equal to 27. That's 3 times 3 times 3, and it's in the denominator, so that gives me a negative exponent, raised to the power of x minus 3. I prefer this method because all of a sudden when I've rewritten things, all of a sudden my base is no longer a fraction. My base is a value greater than 1, so it allows me to keep my inequality the same. Some people, and I have seen it this way, again, not my favorite, some people will do 1/3 2x plus 9 is less than or equal to 1/3 cubed. All of that raised to the x minus 3. Then they have to flip that inequality because all of a sudden my bases that I'm looking at fall between 0 and 1. So they would have the statement 2x plus 9 is greater than or equal to 3 times x minus 3. So if I can manipulate something in such a way that my inequality sign stays the same, that's what I want to do. Now, when we take a look at the back side of this, sometimes we don't have that option, and that's okay. But I do like to rewrite these so that my base is greater than 1. I don't have to think about, do I change the sign? Do I not change the sign? So when I'm looking at the one on the left-hand side, that's the one I'm gonna go with. I have the following statement. -1 times 2x plus 9 must be less than or equal to -3 times x minus 3. From here, I can distribute and then solve. So if I distribute the -1, I get -2x minus 9 is less than or equal to -3x plus 9. Then I can just focus on solving. So I'm going to add 3x to both sides. That leaves me x minus 9 is less than or equal to 9. Add 9 to both sides. X is less than or equal to 18. So on a number line, if this is 0, here's 18. I'm allowed to choose 18 because it's less than or equal to, and I might also choose any value that is to the left of 18. If I chose those values and I plugged it back into my original, see if I can, then that inequality would remain true. That statement would remain true. The left side would always be less than or equal to what showed up on the right side. So let's turn it over and let's take a look at logarithmic inequalities. So here at the top, we have the same statement as the front, that if your log base is greater than 1, whatever inequality that you do see stays the same. But if you have a base that is between 0 and 1, whatever you see gets turned around. And the third statement says the exact same thing with a different inequality. So let's look at 17a. First thing I want to look at is that base. So I do have a log base 2. So that means my inequality is good. Nothing's going to change. I don't have to worry about anything. I do have this coefficient that's hanging out in the front on the right hand side that I have a property that says I'm allowed to move that. So I'm looking at log base 2 of 9 being greater than log base 2 of x squared. Again, looking at those bases, we want to evaluate, say, okay, that's bigger than 1, so my inequality is good, and that means I can focus on just the remaining pieces. 9 is greater than x squared. If I wanted to get x by itself, I could take the square root of both sides. The square root of 9 is not just 3, it's also the negative. So 3 times 3 or -3 times -3 has to be greater than x. This translates to the statement -3 is less than x, which is less than +3. It created like a window. It's got to be between -3 and 3. But before I box this in, I need to think about something else. there are additional restrictions that come with a log. I do know that when I have a log statement, this green section we have talked about must always be positive, which means it's always going to be greater than 0. So even though I have a number line that lets me choose any value between -3 and 3, there might be some values within that window that create a negative log. We can't have those log statements be negative. So what I need to do is look at everywhere that there's an x and evaluate that. So in this inequality, there is no variable on the left side. There's only a variable on the right side. So I know that no matter what, that variable must always be greater than 0. It must always remain positive. Well, if I look at my window here, 0 is in the center. So even though my inequality says I'm allowed to choose numbers between -3 and 3, that would make this statement true. There are specific values that if you chose them, the right side would become undefined. And so we want to make sure that our domain is the most restrictive domain possible, which means if I know that I'm only allowed to have positive integers or positive values inside of my log statement, then instead of having a window that went from -3 to 3, it actually shortens that window to only run from 0 to 3. So my domain, instead of being -3 is less than or equal to x, which is less than, -3, which is less than x less than 3. A more restrictive domain says, well, in all actuality, the only values that I could choose from my window that would keep my logs positive is 0 to 3. Or you could write that in interval notation. So even though I had a very large window to choose from, some of these would create undefined situations. So I just need to narrow my window to my usable values. We'll see that in part B. This one doesn't compare a log to a log. It compares a log to a number. So just like when we were doing equations, we do have to roll it. So 2x plus 1 is less than or equal to, and I roll it, there we go, 2 to the power of 3. My base value is a 2, so that's why I left my inequality the same. So when I go to solve, 2x plus 1 is less than or equal to, well, 2 cubed is 2 times 2 times 2, which is 8. I can solve for x. 2x is less than or equal to 7. If I divide both sides by 2, that 2 is positive, so it's not going to change anything. So my value is x must be less than or equal to 7/2. So here's my number line. Here is 7/2. I'm allowed to choose it because it's less than or equal to, and I'm also allowed to choose anything to the left of that. However, but wait, there's more. I do have a log statement, which means that there is a section that has a restriction. That restriction, 2x plus 1, that statement must always remain positive, always. So I'm going to set it equal, and I'm going to say, can I narrow that window down to a more specific usable value? I solve for x, so minus 1 on both sides. I'm just minusing, so that sign stays the same. Divide both sides by 2, and it says that x has to be greater than -1/2. So even though I could choose any value less than 7/2, all of a sudden, if I choose something below negative 1/2, my inequality here will turn negative. So I've narrowed that window down to just being these values. So even though I had a lot to choose from, some of them would still give me undefined situations. So I want to make sure everything is defined, everything is real, everything is going to show up, everything's going to remain usable. And so my domains, I can choose any values for x that I want as long as they fall between negative 1/2 and 7/2. You can also write it negative 1/2 less than x, which is less than or equal to 7/2. And this should have been a bracket. Okay, so either one of these. So again, we're just working on solving like we have been, but then focusing on, well, is there additional restrictions we have to consider? I have been talking about when your base is greater than 1 or your base is less than 1. Example C has that base being less than 1, so it's 1/2. So when my base is less than 1, my inequality sign gets turned around. So instead of dealing with the greater than or equal to, I'm dealing with less than or equal to. And I've got my two statements because it's a log compared to a log. Okay. Solve for x. So I'm going to subtract x on both sides. Less than or equal to 5. Add 3. So right now I'm allowed to choose any value less than or equal to 8. I'm going to use the solid dot to represent that I could choose that. If I wanted to, I could put a bracket here to remind my brain, hey, that gets a bracket, because y'all saw earlier up here on the question right above it, I forgot about the bracket. So just kind of like just something to keep your eyes, doing the right thing. This time when I look, not only do I have an inequality to check on the left-hand side, I'm going to kind of do these in color. I want to make sure that the left-hand side is always going to remain positive, but I have a second one as well. I have this x plus 5 on the right. It also has to remain positive at all times. So we have this huge window to choose from, anything less than 8. But I need to make sure that whatever value I choose is not going to create a negative log. So if I look at strictly the left-hand side of my inequality, solve for x, I end up with 2x is greater than 3, divide by 2. So this one says, okay, you're allowed to choose anything less than 8, but please just make sure that it's greater than 3/2. Okay, so we've narrowed our window down just a little bit. We also look at the right-hand inequality and say, well, hold on, this log must also be positive, so I need to solve for those values and say, well, what values could I choose that would remain positive for the right-hand side? Well, this one says, hey, you're allowed to pick anything greater than -5. Okay, so if I graph these out, there's only one section in my number line where all three overlap, and that's right here. So if I wanted to give you a domain, if I wanted to be able to tell you, well, what values can I choose for x that work everywhere all the time, I would only be able to pick values from 3/2 all the way up to the number 8. You can also write that in interval notation. So even though I can choose, according to my solution, anything less than 8, if I chose a -6, then this statement would be, the green statement would be bad. If I chose, let's say 1, then the red statement is bad. So what we're doing is we have this huge number line and we're saying, okay, I'm allowed to choose every value in black. Just kidding. Some of these are going to only be here. And then just kidding, it's going to get even smaller than that. And so we want the most smallest window possible, and that's where all three of those are going to overlap. So we have those. I have some practice questions for you. It's very algebra heavy today, but it's really just focusing on making sure that we're able to apply those restrictions, especially to our logarithmic functions. Exponentials, be able to manipulate those, but apply those restrictions to our log functions. We'll do extra practice today and extra practice tomorrow.